Good morning, sir. Today we are here to discuss about band brakes and myself, 18M627 Mono. And what is a band brake? Band brake is nothing but a primary or secondary brake, which consists of a band of friction material. And what does it do is it tightens concentrically around a piece of equipment to either prevent it from rotating or to slow it. The main parts of a band brake are band. The band brake consists of a band. It's a circular piece of spring steel that is rectangular in cross section. Its inside circumference is also linked with the friction material. So the band brake has bosses on each end so that it can be held and compressed. So the second main part of the band brake is the drum. The drum fits inside the band and attaches to the planetary gear set element, and it is to be locked by the band. So the outer surface is machined smoothly so that it can interact with the friction surface of the band brake, and by pulling the open ends of the band together, the rotation of the drum can be stopped. So the other main parts are anchor. The anchor firmly attaches one end of the brake band to the transmission case, and a provision is also provided for adjusting the clearance between the band and drum. And the next main part of the band brake is next slide. And the next main part of the band brake is the servo, and the servo uses the hydraulic pressure to squeeze the band around the drum, and it also consists of the piston. That the servo piston is acted on by hydraulic pressure from the valve body, that is fed through an internal pressure to the case, and the servo piston has a seal around it so that it can prevent the leakage because of hydraulic pressure. So next we can see about the construction of band brakes. A band brake is made up of a rope or belt band which is lined with the friction material, and this band is wrapped particularly around the drum, which has a free end, and it's also connected to a lever. So an external force can be applied to the free end of this lever for braking. So due to the addition of the external force, there is a friction between the band. So due to this addition frictional force, the band is tightened and a tangential force acts on the drum. So the tightening of the wheel, also this tangential force creates a tension in the band and which stops the wheel connected. So now let us see about the working of the band brake. So there are two versions of the band brake: when released and when applied. When the band brake is released, there is no hydraulic pressure applied to the servo, and the drum is free to rotate within the band. And when the band brake is applied, hydraulic pressure is applied to that servo. That in turn tightens the band around the drum, which I've seen before. The tangential force is applied and which tightens. So the result is that the drum is locked in a stationary position, causing output change from the planetary gear set. Basically, there are two types of band brake: simple band brakes and the differential band brake. Let's see the difference between the simple band brake and differential band brake. The basic difference is, in simple band brake, the fulcrum is only one end of the lever, but in differential band brake there are two ends, and the fulcrum is set between the two ends of the lever. And simple band brake is not self-energizing and it is not self-locking, whereas on the other hand, the differential band brake is always self-energizing and self-locking.
Morning, I am Jayhin 18M616. I am going to present advantages of band brakes. With a large coefficient of friction and the angle of wrap, the brake is very effective. Requires low input force to achieve a high brake force. It has a band brakes as a simple construction and its a small number of parts. These features are reduced to the cost of band brakes, and some materials with a lower coefficient of friction have a more consistent and coefficient of across the range of working temperature, and the band brakes requires little maintenance, and it has a more reliable due to some number of parts. The friction of lining is the only part which must be purchased from outside agencies. And in this slide, we're going to see demerits of band brakes. When hot, suffer of loss of brake force, lots of grabbing and chatter. With a with a large coefficient of friction and angle of wrap, the heat dissipation capacity of band brakes is very poor, and it is very sensitive to change in mu, the coefficient of friction. Uh, Using a band material with a low coefficient of friction, increasing the input force required to achieve a given band brakes. The wear of friction lining is uneven from one end to another. The band brakes are used in applications like bucket conveyor chainsaws. They are more popular as backstop device. Thank you.
Good morning, Kaushik. I am going to discuss about for maximum load applied over a brake. The construction of a brake is shown in the slide. The band brake consists of three components: the rotating drum, a lever to be where we apply force, and a band. A band is a steel plate which has a friction lining, and it connects the rotating drum and the lever. A band brake is similar to the pulley. That's why we make use of the pulley equation P1 by P2 equals C power mu theta. Where P1 is the tension over the tight side and P2 the tension over slack side. Mu is the coefficient of friction between the friction lining and the brake drum. Theta is the angle of wrap. The torque absorbed by the brake is given by M P1 minus P2 into radius. We usually calculate torque transmitted in a pulley, but in here we calculate the torque absorbed because the band brake stops the rotation, and hence we make use of P1 minus P2 into or as a absorbed torque. Next slide. In this slide, we have shown the diagram of a free body diagram of how the brake drum works. If we consider equilibrium about the center of the fulcrum, then we can say that P into L is equal to P2 into A, which are the moments acting about the center. And then we can say that P is equal to P2 into A divided by L. If P is the pressure that is imposed by the belt over the pulley over an area of R into W into d phi, then from the diagram we can say that dn, which is the opposing force on the other side, is equal to P into R into W into d phi. And also from the other diagram, the equating the vertical components of the forces, we can get that dn is equals P into sine d phi by 2 plus P plus dP into sine d phi by 2. In here, neglecting neglecting higher order differentials and then taking sine of d phi by 2 is equals d phi by 2, we will be getting dn as P into d phi. Now if we equate both the dn, we will be getting P is equal to capital P divided by R into W. In this case, in order to find the maximum pressure, we need to substitute maximum force for value of P. The force over the tight side is the maximum force acting over the pulley, hence P equals P1 for maximum pressure. Therefore, maximum pressure is equal to P1 divided by R into width of the belt. Next slide. In this slide, there is a in this slide we have a differential band brake. The differential band brake has a special property called self-locking property. A self-locking property is when even there is no force, the band brake is applied is in applied condition and the drum does not rotate. For this to happen, there should be no force acting over the band brake. Similar to the previous condition, if we apply equilibrium condition about the center point and if we consider the moments about the center point to be equal, then we can say that P into L plus P1 into B minus P2 into A equals 0. Hence, from the above equation, P equals P2 into A minus P1 into B divided by L. If we apply the pulley equation in here, and we would be getting that P is equal to P2 into A minus B into per mu. This is obtained from P1 by P2 equals C per mu theta, that equation. And for the self-locking condition, there should be no P. If there is no P, then or P can be negative. Therefore, we can say that if P is equals to 0, then L will be 0 and P2 will be 0. A minus B into e power mu theta will be equal to 0. That will be the condition. Therefore, A less than or equal to B into e power mu theta will be the sufficient condition to say that a belt band brake would be self-locking. Thank you. That's it for.
Good morning, sir. I am Maury Shankar, 18M629. Problems on band brakes. I will discuss about the problems first. Yeah, differential band brake is shown in figure. The width and thickness of the steel bands are 100 mm and 3 mm respectively, and the maximum tensile stress in the band is 50 Newton per mm square. The coefficient of friction between the friction line and the band brake drum is 0.25. Calculate the tension in the band and the actuating force and the total torque capacity of the brake. Find out whether the brake is self-locking or not. Next slide. We will write the Next we will write the given details. Width will be 100 mm and then thickness will be 3 mm, and coefficient of friction will be 0.25, and then the tensile stress will be 50 Newton per mm square, and then radius will be 300 mm. We will convert this into a meter, 0.3 meter, and then next step 1 to find out the tension band. The maximum tension in the band will be P1. Then the formula to find out P1 will be load will be stress into area. Area equal to width into thickness. Then by substituting the given details will be stress, width and thickness value, we will get P1 as 50,000 Newton, and then by using this equation, will P1 by P2 equal to e power v theta. By substituting the coefficient of friction, and then theta will be the angle of the contact between the contact of this band, and then by substituting this P1 value, we will get P2 as 5263 Newton. Next slide, Ram.
Myself, Ravnath S. I am here to explain about the exam problem of the band brake. Band brake working on the backstop principle is shown in figure. The width of the friction line perpendicular to the axis of the drum is 75 mm. In normal operation condition, the drum rotates in clockwise direction, and we have to calculate the minimum value of coefficient of friction between the lining and the drum, so that the brakes acts the backstop brake. If the normal pressure between the drum and the lining is to be limited to 0.3 Newton per mm square, what could be the maximum braking torque? The given is W is equal to 75 mm and P max is 0.3 Newton per mm square, and radius is 150 mm. And first step is minimum coefficient of friction for the backstop brake. From figure B in front page, construct the line OB perpendicular to AC, and OB, therefore OB perpendicular to AC and AE perpendicular to OA. It is the pair of two perpendicular lines. So since the angle between ADB is 30 degree and EAC is 30 degree, we are to find the AB. So AB is equal to OA into sine 30 degree. OA value is 150 and sine 30 degree. So we get the AB value of 75 mm. It is the second division of our problem. It's calculate the maximum braking torque. The formula of the maximum braking torque is P1 is equal to radius into width into P max. Radius is 150, width is equal to 75 mm, and P max is equal to 0.3. So we get the P1 is equal to 3375 Newton. And already we know that previous slide P1 by P2 is equal to 1.75. And substitute the P1 value, we get the P2 value of 1928.57 Newton, and the braking torque formula is P1 minus P2 into 150. So we get the value of final answer is 216.96 Newton meter. And that's all. It's the example problem.